Welcome to Review Lecture 5.1, EMF Source. After this, you should be able to calculate the terminal voltage of an EMF source, determine the internal resistance of an EMF source, determine the open circle voltage or EMF of an EMF source, understand the difference between a charging battery and a discharging battery. Now, EMF sources, the term EMF stands for electromotive force, which is a very archaic term that is no longer used, although we have retained the EMF abbreviation. EMF sources provide energy to an electric circuit by converting some other kind of energy to electrical energy. Many kinds include batteries, which convert chemical energy to electrical, and these are the traditional EMF sources. Generators convert mechanical to electrical. Photovoltaic cells convert light to electrical. To get these to work and to provide energy to an electric device, they need to be connected properly in an electrical circuit. There are several different ways to connect the battery and bulb from a flashlight so the bulb lights up. The important thing is that there must be a complete path or circuit that includes the bulb filament, runs from the positive terminal at the top of the battery, and runs to the negative terminal at the bottom of the battery. Now here, of course, is a battery and a bulb and some wires. So it's the electron flow cycle, which is the opposite of the current flow. Now it runs from the negative part of the battery through the wire. It runs to the side or bottom of the bulb. Now that's one of the connectors to the filament. It goes through the filament inside the bulb, runs out the bottom or the other side of the bulb through the wire to the positive part of the battery, and then through the battery back to point 1. Now, that's the direction of the electron flow. The conventional current, which is the equivalent flow of positive charge, flows in the opposite direction of the negative electrons. Now, usually we only care about the conventional current. Okay, now there are many different ways you can connect up a bulb. There are the unsuccessful ways. In each of these cases, the circuit is not complete. Here, of course, there isn't a complete circuit. Here, it doesn't go through the bulb. In fact, this would short out the battery. You definitely don't want to be doing that. This just basically is just a positive terminal. There isn't a complete circuit to the negative one. Here, this actually is connected to the bulb's glass, and glass is a good insulator, so now the electricity is going to go through the filament. These are successful ones, and in these, there is a complete path for the circuit for the current to flow, and this is the standard one. The current goes from the positive through the bulb to the negative and through the battery. It doesn't matter whether you shorten or lengthen these wires, as long as you maintain a complete path for the flow of the current. So unsuccessful ways, the circuit's not complete. There's no complete path for the flow of charge or current. Successful way, the circuit is complete and charge can flow. In other words, the flow of charge is a current. The energy is transferred from the battery to the bulb and transformed into light. Now, any complete path along which charge, usually electrons, can flow is a circuit. A gap is usually provided by an electric switch that can be opened or closed to either cut off or allow electron flow. The other way you can do it just disconnect it. Most circuits have more than one device that receives electrical energy. These devices are commonly connected in a circuit in one or more of two basic ways: series, parallel, or combination, which is not shown. We talked about this when we talked about capacitors. When connected in series, the devices in the circuit form a single pathway for electron to flow. So in other words, the definition of a series circuit has only one path for the current to flow. When connected in parallel means that there are multiple paths. The paths are also called branches. So the devices in the circuit form branches, each of which is a separate path for the electrons to flow. If you break this circuit here, the flow of current stops and the lights go out. If you break the circuit here or here, only one of the light goes out. So that's the difference between the two. To produce a steady flow of charge, you need a charge pump, a device that, by doing work on the charge carriers, maintains the potential difference between a pair of terminals. An electric circuit needs a battery or generator to produce the current. These are called the sources of EMF or EMF devices. A battery is a nearly constant voltage source, but it does have a small internal resistance, which reduces the actual voltage from the ideal EMF E. The EMF is the electromotive force, and it's written typically with a script capital E. There's many different ways that you might see them in various different places. The big thing to remember is the EMF is the open circuit voltage, otherwise known as VOC. It is also called the no-load voltage, and it's the voltage that you measure across the terminals of a battery that is not connected to anything else, or that is not having a current going through it. Now, the figure shows an EMF device that is part of a simple circuit containing a single resistance R. The EMF device keeps one of its terminals at a higher electric potential, that's the positive terminal, than the other terminal, which is the negative terminal. The current I is the conventional current. The electrons, of course, will flow in the opposite direction. Now, you might see this symbology in some other places. We sometimes represent the EMF device with an arrow that points from the negative terminal toward the positive terminal. A small circle on the tail of the EMF arrow distinguishes it from the arrows that indicate current direction. Some people use this, some don't. I've seen it and not seen it. So don't get too wedded to this. An EMF device in this situation is like a pump in a fluid circuit. The resistance is like the resistance in the pipe running between the high and low reservoir. The potential difference is like the pressure difference between the high and low reservoirs. The current is like the water current in the pipes. And this analogy has been around since Ben Franklin's day. So it's almost 300 years old, and it's amazing how long it's lasted. Now, this is an EMF device in a simple circuit, and this is for Physics 222 students. If you are a Physics 122 student, that is an algebra-based student, please skip ahead one slide to number 11. If you are a Physics 222 student, which is calculus-based, then you're going to be starting here. An EMF device does work on charges to maintain a potential difference between its output terminals. If dW is the differential work in joules, the device does to force positive charge dQ in coulombs from the negative to the positive terminal. Then the EMF, which is the work per unit charge in volts of the device, is the EMF is the derivative of the work with respect to the charge, or EMF equals dW dQ. If you are a Physics 122 student or an algebra-based physics student, you should be on this slide, which is slide number 11. This is an EMF device in a simple circuit. And of course, the EMF device does work on charges to maintain a potential difference between its output terminals. If delta W is the work in joules that the device does to force a positive charge, delta Q, in coulombs from the negative to the positive terminal, then the EMF, which is the work per unit charge in volts of the device, is approximately, assuming a steady state situation, EMF is approximately equal to delta W, delta Q. Again, it's a steady state situation. Now, an ideal EMF source has no internal resistance. In reality, those don't really exist. So an ideal EMF source has no internal resistance. The potential difference between its terminal is equal to the EMF because of this resistance is a resistance of 0. In which case, VAB equals the EMF. In this class, unless otherwise stated, assume all EMF sources are ideal. The EMF E is also called the open circuit voltage or no load voltage, and we'll explain that later. So VOC is the EMF or the no load voltage. This is what you would measure if you put a voltmeter on any battery that is not connected to anything else, or one that's connected to an open circuit and not supplying power or being charged. So in other words, the current in the battery is 0. This is a load curve for an ideal EMF device. The load is related to the current. And this is, of course, the voltage or output of the ideal EMF device. Notice that this is flat and horizontal. So that's because the resistance of this ideal EMF device is 0. That means that no matter how much current is going through the battery, no matter what the load is on the battery or how you're charging it, the output voltage is always equal to the EMF. The voltage across the terminals always equals the EMF. Now we're going to investigate what happens when you have an internal resistance. This is the EMF source characteristics for a real battery during the discharge cycle while it's supplying a current to a load. The real EMF source has a non-zero internal resistance R in ohms that behaves as if it is a separate resistance connected in series with the source. This is a part of the battery and cannot be removed. This grows worse as the battery ages. The potential difference between its terminals is equal to the EMF open circuit voltage only if there is no current through the device. In other words, the battery is not supplying current to anything and is not being charged. So VAB equals E only if I in the battery is 0. When the battery is discharging, that is providing power to the circuit, the output voltage is reduced by the loss in the internal resistance. The relationship between the potential across the terminals VAB, the open circuit voltage E, and the current I in amps is VAB equals E minus IR. And as the current I provided by the battery increases, the EMF falls, and that is shown here in this chart. Here's the output voltage, here's the current that you're drawing from the battery, and this is what happens. As you increase the current, which is increasing the load on the battery while it's discharging, the output voltage fall off by this amount, I times R. I is the current, and R is the internal resistance of the battery. This is for a battery that is charging. A real EMF source has a non-zero internal resistance R in ohms that behaves as if it is a separate resistance connected in series with a source. The potential difference between the terminals is equal to the EMF, which is the open circuit voltage, only if there's no current through the device. That's the same as it was before. So VAB is E if I equals 0. When the battery is being charged, the current is reversed, and the potential needed to charge the battery is increased by the loss in the internal resistance. The internal resistance always fights you. The relationship is VAB equals E plus IR. Now, this is for a charging battery. The one we had before was for a discharging battery. So to charge the battery faster, that means more current, which is a faster charge, you need to increase the charging potential VAB. This is the charge chart for a battery. Notice as the current increases, that is the charging rate increases, this potential here also increases. That is the potential across the battery that you had to supply to get it to charge at that rate. This happens in a car too. The typical open circuit voltage for a car battery is about 12 volts. The charging system of the car supplies 14.5 volts. That's to get the battery to charge in time. The battery would not charge at VAB equals E because then I equals 0. Here's some tips for battery safety. Never try to recharge a battery that is not specifically designed to be recharged. Never charge a rechargeable battery except in the charger it was designed for. Doing either of this or this can result in a fire, chemical burns, or explosions. Never mix new and old batteries. The new ones will die trying to charge up the old ones. Never mix batteries of different types. The higher voltage ones will die trying to charge those of lower voltage. Never dispose of batteries in a fire. Never short out a battery. Be careful when putting a battery in your pocket or purse. Metal objects like keys can short it out, causing a fire and or burns. And you don't want a fire in your pocket. That's really embarrassing. Be extremely careful when jump starting a car with a dead battery. Doing this incorrectly can seriously injure or kill you. Car batteries give off explosive gas when charging, and the sulfuric acid they contain is extremely corrosive. If you short out a car battery, the conductor that you shorted out with can literally weld across the terminals of the battery because they can produce so much current and they heat up the conductor so fast that it basically welds itself to the terminals. In that case, you can't get it off. Your best bet in that situation is to run and call the fire department. Now, batteries can be connected in either series or parallel. The definition of a series circuit is that there's only one path for the current to flow. All of the current flows through each battery. The total voltage is the sum of the individual battery voltages. So if this is a 1.5 volt D cell and that's a 1.5 volt D cell, the total voltage output is 3 volts. The total internal resistance is the sum of the internal resistances. If this has an internal resistance of 0.1 ohm and that's an internal resistance of 0.1 ohm, the total internal resistance is 0.2 ohms. Parallel, which is this arrangement, has multiple paths for the current to flow. Batteries then split the current load, which makes them tend to last longer. The total current is the sum of the individual battery current. So this is producing 1 amp and that's producing 1 amp. The light bulb will be seeing 2 amps. The voltage output is the voltage of the lowest voltage battery, and you should never mix different voltage batteries because one will charge the other. So this one is 1 volt and that is 1.5 volt. The light bulb is going to be seeing 1 volt, and this one will be charging that battery, which could cause a problem. The total internal resistance is lower than the smallest internal resistance. It acts like resistances connected in parallel, and we'll talk more about that later. The combination is not shown. It's a combination of series and parallel, and we almost never see that. A real battery has an internal resistance of 0.1 ohm and an open circuit potential of 10 volts. If this battery is placed in a circuit with a current of 1 amp is drawn from it, what is the potential across the terminal? Well, you're drawing current from the battery, so the potential is going to be lower. And it's going to be lower by an amount of 0.1 times 1 amp, which will be 9.9 volts. Number 2, V equals V open circuit minus IR, and that equals 10 volts minus 0.1 ohm times 1 amp, or 9.9 volts. V is less than V open circuit as expected for a discharging battery with a non-zero internal resistance. A real battery has an internal resistance of 0.1 ohm and an open circuit potential of 10 volts. If this battery is placed in a circuit where a current of 5 amps is drawn from it, what is the potential across its terminal? Well, it's going to be lower than the open circuit voltage, and it's going to be lower by 0.1 times 5, or 0.5. So this should be 9.5 volts, which is answer number 4. So V equals VOC minus IR, or 10 volts minus 0.1 ohm times 5 amps, or 9.5 volts. As the current drawn from a real battery increases, the potential across it decreases as expected due to the internal resistance. A real battery has an internal resistance of 0.1 ohms and an open circuit potential of 10 volts. If this battery is being charged with a current of 5 amps, what is the potential across its terminals? Well, it's going to be greater than the open circuit voltage, and it's going to be greater by the amount of 0.1 times 5 amps, so this should be 10.5 volts. That's answer 5. V equals VOC plus IR for a charging battery. That is 10 volts plus 0.1 ohm times 5 amps or 10.5 volts. To charge a real battery, you must place V greater than VOC across the terminals so the I is greater than 0. In your car, typically V is 14.5 volts to charge a 12-volt battery. If you want to increase the rate of charge, that is, increase the current that's going into the battery, then you can increase this right here, increase the voltage you put across it through the charger. Don't do that unless you know what you're doing. A real battery has an internal resistance of 0.1 ohm and an open circuit potential of 10 volts. If this battery is being charged with a current of 5 amps, what is the EMF of the battery? This is a trick question. The EMF is the open circuit voltage, so it would be 10 volts. Don't fall for that. A real battery has an internal resistance of 0.1 ohm. When the battery is supplying 10 amps of current to a circuit, a voltmeter placed across its terminal reads 20 volts. What is the EMF? It's 21 volts. V equals VOC minus IR, or EMF minus IR. The EMF then is VOC, and that equals V plus IR, or 20 volts plus 10 amps times 0.1 ohm, or 21 volts. The EMF, which is VOC, has got to be greater than V for a real discharging battery is expected because of the non-zero internal resistance. Thank you.